In this video, I want to talk about a particular type of problem involving Riemann integration. So what I've written down here is the definition of the integral via Riemann sums. In other words, I'm saying the integral from a up to b of some function f of x dx, that this is defined to be this limit of the sum of f of xi's delta x. Now, this formula, which is one that you need to understand, and you'll recall in our previous videos we had this nice geometric derivation of this, but what I want you to be able to do is actually apply it in specific problems, and it can work one of two ways. I could give you the function and ask you to write down the sum, or the so-called reverse problem, I could give you this sum, and perhaps the interval AB as well, and ask you what is the function which this particular sum is, say, the right endpoint Riemann approximation of. So it's that reverse problem, the going from the sum to the function, that I want to investigate in this video. Now, first of all, two little things that we want to look at. This definition here, which absolutely you need to know, they also need to figure out how to compute the xi's and how to compute the delta x's. So there's two formulas that are relevant here, and I'm going to do the delta x first. The delta x, this is equal to the b minus a divided out by the n, and the xi here, this is given by xi is equal to whatever the starting point a is, and then you go over 1 delta x, 2 delta x, 3 delta x as you iterate along in your Riemann sum. So in other words, it is a plus some number I times delta x, or if I prefer, a plus I, b minus a, all divided out by n. This formula, which we've defined for the definition of Riemann integration, that you should be able to take this sort of xi and plug it in here, and that you should be able to take this delta x and plug it in there. By the way, this worked for xi denoting right endpoint approximations. This is a very small change that you can think about if we wanted to denote left endpoint approximations. But the standard way to ask this problem is with right endpoint approximations. So what I've written down here is I've got a limit as n goes to infinity. I have a sum of I equal to 1 to n. That doesn't really change. And then I have the tangent of 2 plus 3i times 3 over n. And I'm claiming that I'm using right endpoints. And I have to tell you one more thing. I'm using right endpoints. I have to tell you what the interval is. I have to tell you where I am doing this. So I am going to claim that my right endpoints are going to be used on a specific interval, and I'm going to do, how about 0, 3? I think that's going to make everything look nice. So here's how I want you to do it. Remember we had a formula for delta x, a formula for xi? Let's go in and plug in those values given this interval that we have. So the way this works is that we're going to say that my delta x, well, what was that? That was b minus a over n, so 3 minus 0 divided by n, or in other words, 3 over n. And we can note right off the bat that I have a 3 divided by n in my formula. That this part sure looks like it's going to be delta x. Okay, well, that was certainly interesting. Now let's continue. I can also figure out what my xi is. Well, xi was a. In this case, a is 0, so 0, that's my a right there. 0 plus some number of i's times the delta x, so I 3 over n, or in other words, I 3 divided out by n. And then again, we can go back to our formula that we have up here, and we notice that this part, that sure looks exactly like that. This is going to be equal to the xi. Notice that keep them separate. They look pretty similar, but the xi has the expression that has the I in it. The delta x doesn't have any i's. All right, so now let's try to write down the definite integral that corresponds to this particular Riemann sum. So the first thing I'm going to do is I'm going to do the interval, and I'm going between 0 and 3. And the reason why is because I specified that we were going between 0 and 3 in my actual question. If you didn't specify that, by the way, there'd be different integrals that you can sort of shift them to the left or the right. But if I give you an interval, I'm telling you the 0 to 3. So that's the first point. Second point, I'm going to have some f of x dx here, but let's do the dx first. Dx in the integral. It's sort of the infinitesimal version of the delta x. So if this 3 over n that we had at the top was this delta x, eventually it's going to go away, and what we're going to be left with is that whole thing, the 3 over n that was the delta x, it's just going to go into this symbol dx. All right, wonderful. Second thing that changes is that anywhere you've got an xi in your sum, the xi is going to transform just into x. So I'm going to have this tangent of 2 plus x. So the way I write this is I just say that this is the tangent of 2 plus, and then I'll change to the colors so that we can identify it, 2 plus this variable x, and all of that multiplied by dx. In other words, when going from the Riemann sum into this definite integral that we've written down, that's our final answer here. It was all about figuring out what was the delta x, that was going to go into the dx, what was the xi, that was going to turn into an x, and then everything remained, that was going to go into the function. The tangent and the 2 plus, that was going to go into the function, and the xi turned into the x, and the delta x part turned into the dx. Okay, so that was a fairly straightforward example. Let us see one more, slightly more complicated example. All right, so I have this second example here. It looks like a much messier sum. It doesn't obviously look of the form f of xi times delta x, but it is the same interval 0 to 3. So the delta x and the xi are exactly the same, so let's write them down. So now what I have to do is I have to sort of unravel the messy knot of this particular summation and try to see a delta x and try to see an xi in there, even though it's messy. So the first thing I'm going to focus on, I notice that I actually occurs in 2 places in the sum, but I think the closest looking one is this guy right here, the 6i over n. Because 6i over n and 3i over n, they're pretty close. Indeed, this looks like twice xi. And that's all right, because if I was translating this into a function, this would turn into 2x. So that portion of it I like. Now, here's the tricky thing. I've got this remaining I, which is sticking out here on the right-hand side like a sore thumb. And then, while I'm at it, I've got this weird I, but I don't have another 3 over n anywhere. I don't have an obvious delta x. So what on earth is going on? Now, what I think I'm going to do is that if I look at the formula, the xi is equal to I 3 over n, look, I just have this I by itself. So why don't I try and identify what I is supposed to be here? Okay, so I is going to be equal to xi divided out by 3 and multiplied by n. So that's a formula, and I can take this and I could substitute it in. So why don't I try that? Let's see what happens if I'm going to go and write out this. Okay, so now as I've written it down, I've made those 2 changes, that 6i over n, I replaced that with a 2xi, and the I on the bottom, I replaced that with this xi times n, all divided out by 3. Okay, so making a little bit of progress. Now, next point. I still have to figure out where is my delta x. My delta x is 3 over n, but look what's happened. In transforming this I now can see it. If I take that 3 and that n, this is going to be my delta x. So I'm making a lot of progress here. Now, what I have is I have a bunch of different xi's, and I also have a delta x. So I think I can take this now and I can go and try to write out what my definite integral is going to be. I'm going to say that this is equal to the integral from a up to b, so a was 0 all the way up to 3. I know what's happening to the delta x. The delta x is going over and it's transforming into just a dx. And then I know that the xi's turn into x's, and everything else that remains goes into my function. So the xi's are going to x's, everything else is just going into my original function. So what does this look like? Looks like I got a 9 up here on the top. Nothing ever happened to that. It was just sort of being there annoying. I've got a 2, and I'm going to even take the first 2 over here and leave it there. 2 plus 2 squared. And then I'm going to put in my xi's turning to x. I've got 1x there, and I've got an x down here on the bottom. And so there we have it. We have now the definite integral corresponding to the right Riemann approximation on the interval 0, 3 of this particular limit of some messy expression.